So we start a new lecture, this time on the analysis of variance, or ANOVA. Okay, so ANOVA stands for the analysis of variance, and it is a good technique to answer questions of whether a continuous variable depends on the value of a categorical one. So for instance, does the maximum temperature in Madrid, that is a continuous variable, depend on the year, which is categorical, or temperature on month, or month and year, and so on. So here we have, for instance, the plot, the histogram of the maximum temperature at Retiro, and so here is the temperature, here is the number of observations. So for instance, if we decompose this data in something that depends on the year, we don't see any particular pattern. Might be that the median, that is this red line, is shifting up, but the mean doesn't, or at least the range of values doesn't seem to have any particular value, any particular pattern. If we look at the months, now we do see a pattern. So in January it is colder, while in summer it is much hotter, so as expected. Okay, so let's try to put numbers on these observations. So here is another example in which we can see what is the expected value of the electricity generated by nuclear power plants, and we don't see that there is any change over the time of the day. But if we look at the demand, there is a change, and then we can see that there are some valley hours like 5, 6 in the morning. There are peak hours like 9, 10 in the evening, and if we ask what is is there a dependency of the continuous variable, that is the electricity demand, as a function of the time of the day, and this considered as categorical variable like 1, 2, 3, but distinct values with no numerical relationship between them, then ANOVA is the right tool to do that. So in ANOVA is a regression problem in which the predictor variables must take discrete variables, and they can be continuous by nature, but they have been discretized. For instance, here the time is continuous by nature, but it has been discretized into distinct values. Then ANOVA can be regarded as the studying the variation of the expected output conditioned to the group of the factors, and we will see in more detail what this means. But basically it means that if we group by hours, so let's say that we have 9 hours, what is the expected value of all the observations at 9 hours, and then at 10 hours, and then at 11 hours. So in general, what we are doing, for instance, if we have 2 factors, is we have x1, x2. For every combination of x1 and x2, we compute what is the average of all the observations with that particular combination. So for instance, this point here would be f2, and then we analyze. ANOVA analyzes whether there is a pattern, an overall pattern in all the samples, or otherwise there is no specific pattern and all the samples are equally. Okay, so, or they have equal value. And then there are different kinds of ANOVA. and depending on the number of predictors we are using. So we have one-way ANOVA, two-way ANOVA, n-way ANOVA. The difference is how many predictors we have. So in this problem we have just one predictor, that is the time. Here we have two predictors that are x1 and x2. So the first one is an example of one-way ANOVA, and this one is an example of two-way ANOVA. And then we can generalize to more than to any number of factors. And when we have factors, a different number of factors, we can compute interactions, and we will see this concept later. But we can think of them as combinations of the factors or the levels of the factors that are particularly good or particularly bad. And just a remark, when we are using one-way ANOVA, normally we use more than two groups, so three or more. And the reason is that the two groups is covered by a t-test. So the results that you get from a two-group t-test should be the same as the one-way ANOVA with two groups. Okay, so let's look at the one-way ANOVA. So let's say that we have observations of x and y, and x takes categorical variables like g1, g2, g3, and y a continuous variable. So we have 9 observations. They are distributed in the 3 groups with 4 samples coming from g1, these 4, then 2 samples coming from g2, and 3 samples coming from g3. And then the ANOVA model says that the observation at a particular group is a mean of that group, and the mean of that group is decomposed into terms. One is the overall mean plus some extra value coming from that group. So if there is no difference between the groups, all these extra values, alpha 1, alpha I, alpha m, will be 0. And then there is some noise. Okay, so the noise, as always in all regression terms, in all regression problems, we assume that they are Gaussian with zero mean and standard and some variance, and ANOVA makes the assumption that the variance in all groups are the same. And we can look at this plot to better understand the ANOVA model. So we have the overall mean that is represented here by this red line. So we have the average of a group is the overall mean plus some extra contribution coming from the group. So if you are in the first group, your extra contribution will be positive because the overall mean of the group is 5, while the overall mean of the whole population is 2.5, let's say. So this extra 2.5 is coming from the alpha 1. But then in the alpha 2, the mean of the group is 1, the overall mean is 2.5, so the extra coming from the second group is minus 1.5. And so because these two terms are deterministic and the only one that is random is the residual, so the residual is assumed to follow Gaussian with zero mean and a given variance. So the observations within a group, because this is constant, is the mean of that group. So they are assumed to be Gaussianly distributed, and with the mean that is given by the mean of the group, that would be mu plus alpha 2 in this example of the second group, and then the same variance as the residuals. So ANOVA, even if the underlying function is or the underlying predictor is continuous, it gives us a lot of freedom to model different responses. So for instance, if we are using linear regression, the dependence of y on x can only be a line, and this is the representation that we have. So the expected value of y given a particular xi value is beta 0 plus beta 1 xi. But now, because the ANOVA model, every group can have a different value, we are not restricted anymore to lines, so we can have very funny shapes, and we are much more free to represent any kind of dependence. And there is another difference, that is the nature of the predictor. So here you can see that it comes only at discrete points, so we don't have any observation between 0 and 1, any observation coming from 1 and 2, and so on. So in between we cannot have observations, we have to group them at discrete values. Then how to estimate these parameters. So this calculation here, they are shown for groups or ANOVA experiments in which all the groups have the same number of observations. Okay, so we can calculate the mean of any one of the groups. So the mean of the group is just the mean of the observations of that group. We can compute the overall mean, that if all the groups have the same number of observations, can be calculated as the mean of the means. And then we can compute the extra. The extra is the difference between the mean of the group minus the overall mean. And there is a consequence of this calculation. Actually, it is not a consequence, it is a restriction that we put at the beginning of the model. That is that all the alpha i's, all the extras, have to add up to 0. And then with this explanation, we can decompose the sum of squares into different components. Some part of this component will be explained by our model, the other part will be the residuals. Okay, so the total variability that we observe in our data can be defined as the difference between every observation and the overall mean. And since we don't care whether the difference is positive or negative, we can square them. And then the variability within the groups can be calculated as the variability or the difference between our observations and the mean of the group. So here note that it is the overall mean. Here we are using the mean of the group. And then we can also calculate what is the contribution, what is the difference between all the groups and the overall mean. And we do that for all observations. So here the observations are encoded by the ij indexes, and we have to sum over all I over all j. Over all I means all groups, and then all j means all observations within a group. And here we also summing for all observations, but now we are, for every observation, we are measuring what is the difference between the group mean and the overall mean. Okay, so there's a property that says that the overall variability, the total variability, is the sum of the residuals, the sum of the squares of the residuals, plus the sum of the squares of this explained variance. This is explained because it is explained by our model. So our model tells us that for every group we should observe something that is mu I hat. So that means that every time we have a new observation from the group, our model, the ANOVA model, tells us it should be around the mean of the group. And you don't see the mean of the group, you see something different. the difference between what you observe and the mean of the group is the residual, the explained part is the mean of the group. Okay, so now we can compute something that is called mean squares, and the mean squares is the ratio between the sum of squares and the numbers of degrees of freedom that you have used to calculate that sum of squares. So let's say that we have m groups. So for m groups, and because of these, we have to calculate the mean of m groups. So that means m alpha I parameters. But because there is this restriction, we are not consuming m degrees of freedom, but we are consuming m minus 1 degrees of freedom, because once you tell me m minus 1 of these alpha parameters, I can automatically calculate the last one. And then for the residuals, if I have n observations, I have n minus m degrees of freedom left for the residuals. Okay, so we make these two ratios, and this is an estimate of the variance explained by each one of the alpha I parameters. This is the variance explained by each one of the residual parameters. These epsilons, we can also estimate these epsilons here. You can also estimate, and that is an estimation of what is the variability explained by each one of those parameters. So the ANOVA null hypothesis is that there is no difference between the groups. So the mean of all groups is the same, while the alternative is that there is at least two groups that for which the mean of the two groups is different. And the way to test this null hypothesis is you calculate the F statistic, and the F statistic is just the ratio between these two sum mean squares that we have calculated before. And under the null hypothesis, this ratio should be distributed as an Snedeker F with n minus 1 and n minus m degrees of freedom. And this is the shape, more or less, of this kind of functions or distributions. And then our f will have some particular value, let's say this one, and or here it is mark 7.71, so let's say this is ours. And then we have the acceptance region, that is the region on which we cannot reject the null hypothesis, and if our f goes beyond this threshold, then we would reject the null hypothesis. And just a reminder, the p-value is the area from the observed f and infinity. So all this area here would be the p-value. Okay, so we can organize all this information into a table. This is the typical ANOVA table. So you have the different predictors. Here we have, in one way ANOVA, we have just one variable, so this is the groups. And then we have the residuals, and then we have the sum of squares, so we have the sum of squares total, the ones associated to the error, and the one associated to the groups. And then the number of degrees of freedom that we have. So if we have n observations, in total we have m minus 1. For the groups we have consumed k minus 1, and the remaining n minus k goes for the residuals. Then we have the mean squares, that is the ratio between the sum of squares and divided by the number of degrees of freedom. Then we calculate the f, and from the f we can calculate the p-value. Here is an example. So here there was a total variation of 55, a total sum of squares of 55, 50 coming from the groups, 4.5 coming from the residuals. This is the number of degrees of freedom, so there were not many observations. This is this example here. The first one that we had only 9 observations. So for these 9 observations, we have 8 degrees of freedom. We have consumed 2 to estimate the contributions of each one of the groups. We had 3 groups, and the remaining 6 go for the residuals. And then we can calculate the mean squares, the F, and the p-value. And since the p-value is very small, we reject the null hypothesis that there is no difference between the groups. And this is clearly seen on the plot, where we see that not all the groups have the same mean. Sometimes if you have very clear plot like this one, but very few data, even fewer than what we have now, then you cannot reject the null hypothesis. You cannot reject the hypothesis that the differences that you are observing are just produced by chance. Okay, so let's see a couple of examples, or a few examples. So in this example, we have 1000 observations, and we construct a y variable that is simply noise. So you see all the groups have 10 as mean, and then the standard deviation of the noise, that is 0.5, and we will have 1000 observations. We distribute in 4 groups, A, B, C, D, and these are all our observations, and these are the different groups. And what we see is that most of the variability is coming from the errors, and when we compare the mean squares, the ratio is almost 1, and the p-value is very high. So we cannot reject the null hypothesis that there is no difference between the groups. That is actually what we observe. And if we have fewer data, but still we don't see differences between the groups, so the y has been constructed without any difference between groups, then simply by chance we observe differences in the different groups, but the technique is still able to recognize that these differences are not significant. They are not above the level of noise, which is much higher than these differences. Okay, so now we have some differences between groups. So we have noise that has a mean 10 and some standard deviation, but now the output depends on some x that we have previously calculated here. And now we see in the box plot, we see that there are differences between the groups. And if we calculate the total sum of squares, most of it are coming from the groups, and the mean squares is extremely significant. So that means that the factor ABCD really makes a difference between the groups, and we can have the same thing, but now with much more noise. So we can see that the noise here was 0.5, now the noise is 10. So we have much more noise, and then most of the variation is coming from the noise, it's not coming from the groups. But if we normalize by the number of degrees of freedom, now the groups still are significant. But this already highlights something, that the ANOVA, as many other hypothesis tests, at the end is a matter of signal to noise ratio. So the signal is the difference between the groups, and we observe some difference. Here the difference is almost the same, but now, because there is so much noise, it is much more difficult to show that this signal exists within the noise. So the more noise you have, the more difficult it will be to show that there is a significant difference between groups. So this would be all for the one-way ANOVA, and next lecture would be about the two-way ANOVA.